I've had the pleasure of working with her towards her PhD, and she has been the most amazing student ever. She has done excellent contributions to polynomial optimization and the analysis and application of optimization algorithms, or of these polynomials inside optimization algorithms. She has won various prizes for her research, including a Leslie Fox Prize in numerical analysis awarded by the Institute for Mathematics and its Applications, the IMA. She is now, as you know, one of the AI Hub postdocs, and she is now thinking about using AI for polynomial optimization and also other projects. So over to you, Kate. Thank you.
Thank you very much. Thank you very much, Cora, my supervisor, for this amazing introduction. So today I want to share with the AI Hub. I think the majority of the talk will be on my PhD studies. It's more on how we use tensor method for non-convex optimization. Till the end of it, we're gonna share a little bit of a trial of how we use AI integrated approach to approach our problem. It is so for now it is still just a little trial, and I would really want this talk to open up more discussions and collaborations across the hub of how we can use more of those AI techniques for our problem. Okay, so I will start. So basically, this is the optimization problem that we are looking at. We are looking at an unconstrained non-convex optimization problem. This f, we assume, is like a black box function, so we can only get certain points, certain function evaluations of this f. And we assume f is basically a sufficiently smooth and a bounded below continuous type of function. So this kind of classic minimization optimization problem, many first order and second order method has been done. For example, like steep descent, SGD, Adam. For second order method like Newton, ARC, BFGS. What we are more focused on in my PhD study is third order method. That's why we call beyond second order method for optimization. For third order method, what we do is that we get a Taylor approximation. So this is basically a polynomial approximation. When we say third order, P will be 3. If higher order, it can be any piece order approximation. We get the piece order approximation of this smooth function here. This is the Taylor part. And then we add a little regularization term. So this is a p plus 1 order degree regularization term. So this is a polynomial Taylor approximation, and this is p plus 1 order regularization term. When p here is odd, then this will be like an even regularization term, then the whole thing will be a polynomial. And then this regularization term is very important because it fits into the adaptive piece order ARP framework. In the ARP framework, we are able to adjust sigma. So sigma is a positive weight, it's a regularization term, and we are able to adjust how large or small sigma is so that the algorithm can progress and guaranteed to converge for the optimal stationary point of f. So usually sigma, when sigma large, it is more regularized. The landscape of MP will be more regularized, and every step will be smaller. And when sigma is small, it is a more aggressive model, allow for longer step size. So why are we so interested in high order method, and why we use this ARP framework? There are many theoretical benefits. Prior to my PhD studies, there are many Katis, Coin, and Nesterov. They all proved in the field that for piece order method, we all know Newton has quadratic rate. For AR3 third order method, it has cubic rate. For piece order method, it has piece order local convergence rate. So in theory, the local convergence rate is very good. And in terms of worst case evaluation complexity, so starting from for a non-convex landscape black box function, starting from any point, it's guaranteed to converge. What is more is that it's guaranteed to converge with this complexity, epsilon minus p plus 1 over p. So you can see that when p increases higher order, this complexity increases. This is also the optimal global convergence rate within piece order class. So to show a bit of numerical motivations, so these are two functions, Silom and helping functions in this paper, and this plot is done by Liu Yang and Wassel, who's a postdoc and a former postdoc and a former PhD student, also in Oxford Numerical Group. So in these two plots, we see that you can see this function is like a snow mountain, and the blue dot are the first order method, black dot are second order method, and the red dot are third order method. So the oracle calls, the number of evaluation iteration needed for third order method is much less. So sort of like third order method is able to identify the curvature, tensor direction, and move down the hill. So it takes much less iterations and evaluations to converge to the minimum of this function. In terms of CPU time for these two functions, then AR3 method, third order method also needs less CPU time than second order method. But these are just two small-scale numerical motivations. For a more larger scale problem or more general problem, the key question that I faced or I spent my PhD on is on how to efficiently minimize this piece order subproblem with this piece order Taylor approximation, a piece order polynomial plus a p+1 order regularization term. So I started my PhD. Cora warned me that this is a difficult question because Nesterov have proved like 20 years ago that maximizing a cubic polynomial over a unit ball is NP hard. However, our problem setup is a bit different, as in like we do this regularization term and it turns out to be very special and useful. And also like convexity for polynomial of degree 4 is also NP hard. So we have this polynomial optimization problem and it is non-convex, and that's basically what we are trying to explore. So in the first half of my PhD, I sort of like studied a bit of using different iterative method, secular equation approach, generalized non-eigenvalue kind of approach to minimize this kind of problem. And it also leads to a few papers which finds local minimum for this kind of MP model, polynomial model, local minimum for this polynomial regularization problem. And today I'm going to talk a bit more on how we find the global minimum for this problem, for this regularized polynomial problem. Is there a trackable, so the key theoretical question we are looking at is that, is there a trackable technique? Is there a polynomial time kind of technique for globally minimizing the regularized polynomial problem? So this goes into a lot of prior work by Lazelle, Ahmadi in polynomial, Nia Parabolo in polynomial optimization community. And also it leads to actually like the famous Hilbert 17th problem. So in Hilbert's problem, it asks, if we have a non-negative polynomial, if this polynomial is non-negative, can we express this into a sum of square function? Sum of square function meaning that, for example, Q is polynomial, it can be expressed into just like sum of squares of polynomial. So clearly, if a function is this form, is a sum of square, then it is non-negative. However, if a polynomial is non-negative, is it sum of square? And why do we want to express it into sum of square? Is because if a polynomial can be expressed into this form, into sum of square form, then it's shown that this polynomial can be expressed as a SDP problem of polynomial size, and therefore the SDP can be solved in polynomial time. So that's why it's very important for us to understand whether our polynomial, our subproblem, after shifted by global mean, can it be expressed by sum of square? So the answer, if it's a general polynomial with no structure, no regularization term, just a general non-negative polynomial, the answer is given by Hilbert. It is negative. So a non-negative polynomial generally cannot be expressed by sum of square. And there is a counterexample given by him. However, our problem is very special because we have this regularization term. Of course, we assume P is odd here, so this is an even Euclidean norm, and you can expand it into like regularization, into polynomials. And also because in the ARP algorithm, we can adjust our regularization weight sigma, right? So we have two special structures to explore. One is we have this regularization term. Second, we can have sigma we can increase sigma. We have the freedom to increase sigma. So our question narrows down to, can we have this polynomial with regularization with large sigma? Can we make it into sum of square? Can we make it? If we can make it into sum of square, then there is trackable techniques in solving it. The answer for this is actually the answer for this kind of problem. We will prove through two papers that it is yes. So it's divided into two different cases. So we give positive answer to this. Basically, when regularization weight is large enough, polynomial of this form, regularized polynomial, can be expressed, non-negative regularized polynomial can be expressed as a sum of square. Therefore, we can use trackable STP with a polynomial size to solve it. So there are two cases. I will go through one by one. First case is here. It's an easier case, is that when the polynomial is locally convex. So at the base point, I'm locally convex. Then this blue line is when the regularization is small. Through gradually increasing regularization, you can see that the polynomial go to this red line and go to this yellow line. It becomes more and more convex, more and more regularized, more and more well-behaved. This is just a 1D polynomial, just for illustration. In practice, this is true for all dimension. This work is the first line of work is proved by Ahmadi in 23. So he proved that for a convex polynomial, when you increase it enough, it becomes SoS-convex. So so sort of like if it's the polynomial, if sigma is small, it's not convex. Increase it is first convexify it, then become SoS-convex. Therefore, can be solved in STP of polynomial size. This is the work we have in 26. Like we proved that we sort of like proved it, extended it into a much more difficult landscape when it is locally non-convex. So firstly, if you look at this blue line, this is univariate fourth degree quartic polynomial. When it is non-convex, clearly it's very non-convex. When you increase regularization here, you see that even this red line and this yellow line, it will never convexify. It will always stay non-convex. And non-convex is always much harder in the optimization landscape. It will stay non-convex near origin, always non-convex. However, even though it's non-convex, at one point, when regularization is large enough, then non-negativity and sum of square exactness, they coincide. So there is going to be like a few pages of rather technical proof. So I'm just going to give like a proof sketch of how we sort of prove this. It is very interesting because it sort of like aligns this polynomial optimization and global optimality theorem together. So for example, I have a fourth degree polynomial. This is a quartic fourth order regularization. So here, this is Euclidean norm raised to power 4. This is clearly a polynomial. And I want to do a Taylor expansion of it at the global mean. So assume I know where the global mean is, S star. And then I Taylor expanded at S star. It's fourth degree, so I can just do fourth order Taylor expansion, and it is exact. So this is a first order, second order, third order Taylor. The next thing is that the fourth order Taylor expansion is going to recover me the regularization norm. And then I'm going to use my optimality condition. So we have given sufficient global optimality condition for this kind of polynomial. So firstly, if we know S star is global mean, of course, it's a stationary point. So the gradient term will be 0. And the second order, because global mean is a second order local mean, so the second order will also be PSD. So this will be a PSD matrix. Further, we will need to use the sufficient global optimality condition, which shows that this B matrix of this form, which it has a similar expression as a second order term, but slightly stronger. So we will have shown that this B matrix, which contains the Hessian term, tensor term, and this regularization term inside, the sufficient global optimality condition is that if this this is a first order. This is equivalent to first order optimality condition, like this gradient term is 0. And then we show, and also if we also have the second order global optimality condition as this B matrix as positive semi-definite, then we will basically know that S star is global mean. And if these two conditions is satisfied, we will be able to show and split up that M3 minus S star is SOS. So in short, it means that in short it means that when we have this condition of this B is an n by n matrix. So when we have this condition of like this this matrix system and the positive semi-definite of this matrix system, then we can show that this quartic polynomial is sum of square. So to complete this train, the only direction to complete this line, the only missing direction is that when can I put a necessary sign here? When can I say when S star is global mean, then I guarantee to have this condition to hold. And it happens that this direction will be completed for large sigma. So when sigma, or in other words, when sigma is large enough and I know S star is global mean, I will know my B S star is always PSD. Why would I know that? The proof is rather tedious, long, but you know, like just looking at this expression of B matrix, we can, you know, draw a little bit intuition out of it. So the whole thing, most important term in the B matrix is this term here. And when sigma is large, this one will be large and positive. However, S star, which is the size, the norm of the global mean, S star will tend to 0. As you can see that in earlier plot, you know, when you increase regularization, you see initially global mean is here, then global mean is here, then global mean is here, right? So when you're increasing regularization, then S star, the norm of the global mean, will close to 0. If regularization goes to infinite, then this function will just reduce to like 1 point, then S star will basically go to 0. So the key point here is that sigma is going to infinity, S star is going to 0. Which one will be dominant? So S will have sigma times S star square, this whole term. Will this whole term give us PSD for B, or will this term collapse to 0? This is exactly how we prove it. So we prove that when G is non-zero, when gradient is non-zero, okay, this is some mild assumption, then we will have this term. So we will have S norm, S star norm is of epsilon, is of sigma minus 1/3. So it means that this sigma S star square term, this term will not collapse as sigma goes to infinite. It's just enough. It's just enough that the decrease in size of S star is not that much, and the increase of sigma is more. So sigma is able to dominate this B matrix, and this B matrix will be PSD for large sigma. And note that we give an explicit bound for sigma here. So like we actually give a bound of how large sigma need so that it becomes SOS. And this bound for sigma depends on coefficient of GHT only. So it doesn't depend on coefficient of S star, which we assume that we don't know a priori. This is a little plot to show that in this plot, this horizontal axis is the size of sigma. Vertical axis is the size of S star norm. And this line is basically a theoretical line of sigma minus 1/3. So we see that for large sigma, S star indeed scales like sigma minus 1/3. This is for large ones. And this blue dot here shows that, means that my polynomial become SOS. And this red dot here, means that my polynomial is not SOS. And for size of sigma, from 0 to 20, my polynomial is not SOS. And the larger sigma going above 20, my polynomial starts to become SOS. And the sigma and the bound, the rate of sigma and the star starts to, you know, match my theoretical rate. Okay, so This is one page also a bit more going into the theorem a bit more. We proved this using, so we proved the previous part of it using a lot depending on the optimality condition, the global optimality condition, following the ways from like a cat is going and toying of an S lemma, and how we use this kind of B matrix and the first order, second order of global optimality condition. And this page is much more, I think, more based on a global optimization point of view. So global polynomial optimization point of view. So in global polynomial optimization, the whole point is that when the matrix, when we get the sum of square expression, we say we can make it into a SDP, tight SDP formulation. And this is this Q matrix. And here, phi 2 is all the monomial bases up to degree 2. And we can multiply. So these are the, so here, this is monomial basis, this is monomial basis, each of it is of degree 2. So multiply together, it gives a first order polynomial. And this big Q matrix here contains all the coefficients that we need. Of course, the coefficients here depends on S star, the global mean. But if we know S star, we'll be able to give this, the full expression, the full Q expression of this. We can basically give the explicit trackable tight SDP expression. And this is for, of course, when for sigma large, this expression is true for all the time. But when sigma is large enough, Q become a PSD, and this really becomes, like a SDP formulation to solve. Following that, so following the general theorem, general theorem we then later give like a few subclasses of polynomial that is SOS. So basically we find that basically you find that for univariate bivariate quartics, according to our theorem, is the polynomial is sum of square for any sigma. So no need sigma large for any sigma. And in here, equivalence equals non-negativity. This is matching Hilbert's result. Moreover, we find a few special cases. For example, when there are special structure on the tensor term, we can relax the condition of regularized enough for any sigma. In this class of polynomial, we will have equivalence of sum of square and non-negative. Another little interesting link that we want to talk about is that we find that this Euclidean norm regularization is very important. And in some other tensor models, for example, like Chernobyl tensor model in 82, a classic model, what he uses is using separable norm. So like Sj to the power 4, some like this kind of norm, instead of our Euclidean norm. And for the separable norm, then what is shown is that in this case, it will not be sum of square for all sigma. No matter sigma how large, this will not be sum of square. However, in this case of Euclidean norm with G non-zero, then we can get sum of square for large enough sigma. So this actually goes back to, sorry. So this goes back to like one of the results I mentioned a bit earlier when we talk about that Nestor, when I started my PhD, and I know of this bad news that Nestor proved maximizing or minimizing a cubic polynomial over a Euclidean ball is NP hard. But we proved that when sigma is large enough, quartic polynomial can be solved trackably. Isn't that a contradiction? And it turns out that the main point is that Nestor's NP hard result is using Euclidean ball, and it doesn't have the freedom to choose radius. So it is a bit like the difference between the trust region framework and the regularization framework. So for us, I guess the overall picture that is that it's very important for us to have this Euclidean norm regularization, and also very important for us to allow increase the sigma size, increase the size of Euclidean norm regularization. I will talk through this a bit faster. So on here, when we have, now we sort of like know how to minimize quartic polynomial, a quartically regularized polynomial. When regularization large enough, we'll be able to, get as tractable SDP, right? So this is linked with another paper. In this paper, we give a global framework. So sort of like, if we have this kind of, third order polynomial, we have third order Taylor expansion and regularization, then how do we do an iterative algorithm step by step to be able to converge to the local mean of the function outer iteration f? So how do we use this under a global framework? So this was by another another paper, and the setup here is slightly different. So it uses quadratic regularization term to make the inner problem, to make the subproblem SoS-convex. But the whole idea is like this. The whole idea is like this. So we fit either it's SoS-convex or else SoS-Taylor model. How do we fit it into not only just polynomial, but using that to find minimum of general function f, right? So the way we do it is that at any test point, at any trial point, we sort of do a Taylor expansion. We get the first order, second order, third order Taylor polynomial of this function. We extract it, we get it, and then we add this regularization term, and then we are able to solve this problem because we know that this problem is SOS or SOS-convex with sigma large enough, right? So we can solve this problem trackably. And then we have this performance test. We're gonna test. When we solve it, we get a new point sk, right? And we move to this step, and we check whether this is a good step. This is like similar to the ARC framework, trust region framework. So we check whether it's a good step. We will compare the function value decrease to the Taylor polynomial decrease. If this value is good, is a successful step, we will accept it, and we will decrease regularization. We'll be more aggressive on next step. Otherwise, we reject it, we'll increase regularization, and then we will solve again. So this framework, we proved the global complexity and global convergence of this framework. We proved that basically, if we stay here, so this model is locally, we can approximate our function f by this Taylor MC model. So by increasing it, there's the upper bound. When we increase to a certain point, the step will be successful. If we accept it, and we will be able to move to the next step. And also prove that every successful iteration will give us monotonically function decrease, and we will be able to reach to the stationary point of f. So this is some of the complexity bound we give. In the strongly convex case, we have very good complexity, and in the in the locally convex iteration, we will have good complexity for the SOS convex framework. Okay, so here is a little bit of the numericals that we want to share. So it's also, this is relatively preliminary numerical results. On this page, what we wanna show is an interesting thing is that for this Bell function, which it has a unique global mean, it is a highly non-convex function. It has like long narrow valleys, and it's a difficult test function for many first order, second order. So to test whether it converges to global mean, it is a test function for first order, second order, and third order algorithms. And here in this plot, we plot the basin of attraction. So these are random, we give random initialization in the square of -4 to 4. So if it is blue, it means that, for example, starting from initialization here, it doesn't converge to global mean. If it is yellow, it means that it converges to global mean. So we can see that the basin, so this is a classic Newton method, and Newton method is a very local method. So usually it doesn't converge to local, it doesn't converge to global mean. This is third order Newton method, meaning that we have first order, second order, third order term, but we don't have regularization. And it increases the basin of attraction a bit more. And these two are our AR3 plus SoS-convex method. And we see that the basin of attraction is much larger now. It's different and it's larger. So the regularization really helps to move the iterate towards a global mean for this example. And then I'm gonna maybe use the next like 5-10 minutes to talk a bit about like AI integrated approach that we tried on our problem. So this was a relatively this was a approach we do like around like 2 years ago. So like now a lot of models are different. So this was inspired by one of the paper by meta scientists. What they do is that they use LLM, they use symbolic transformers to identify the non-negativity of function for globally ethno functions. And then we started to think about whether we can do it to identify the SOS property of ARP polynomials. So note that for most of the current ARP solvers, for example, like SOS tools and YAMIP, you can only do small scale examples with N and a D not much higher than 10. So we're sort of thinking about like, is there other ways we can use AI integrated approach to be able to give us some insight on the SOS nature and go to a higher dimension. So this was like the motivation of this project. And we did a little test. So we generated different test sets with thousands of small test sets, only 1,400 polynomials. And then we give different SOS reasoning, which includes our theorem and includes a step-by-step sort of like a pseudo-coded algorithm to identify whether the polynomial is non-negative, non-SOS. So yes, so this is sort of like the thinking process or the pseudocode process we give it to it. So initially, if we don't give it anything, then LLMs, they are very bad. They only have 50% chance of getting it right. They're very bad in identifying a polynomial with sum of square or not. And then after we give like this, the theory guided approach and the training, then we see that across different models, it was older models we tested 2 years ago. So we are only on GPT 4.0 and then Llama 3.1. So baseline accuracy is only 60%. And then after giving SOS reasoning, then there's across models, there's increasing accuracy. Across all tested subclasses, there's also increase in accuracy. We also did a fine-tuned model, very small fine-tuned model that is able to basically give a similar, perform comparatively similar answers for this kind of problem and with similar kind of accuracy. So this is a very preliminary trial which we did like a few 1-2 years ago. Now we are following this work. There are more approaches we see. So for instances, there's one paper on neural SOS, which they train much larger test set, tens of millions of polynomials, and to be able to, using very similar approach, but training nets to be able to identify whether we can get a pruned basis. For example, like suppose this is the monomial we have, then of course you see that it doesn't contain all the monomial bases. So how to train the nets to prune away the unusable bases so that we can reduce the size of SDP. So there was some follow-up work on that, and this is also an active topic that I'm researching now. And now we have a slightly more theorem developed, and now we're using a sort of like theorem-guided way to see how to prune this net and how to do the AI integrated reasoning. So one interesting thing is that interesting example that we gathered from Kunwen 14b. Back then we tested, we always wanted to think about the interpretability of this process. So we asked several questions to the trained net. So we asked them whether they can give us a valid example of a non-negative, not SOS polynomial. So just then I mentioned that non-negativity is not, non-negativity is not equivalent to SOS. That's what Hilbert proved, right? And actually, the first counterexample of this was discovered 30 years later after Hilbert's proof. But it was like it was all like 100 years ago, right? And then we asked Quinlan to find us a new counterexample not found in the literature that is non-negative, not SOS. And it returns us this example, a very simple example, and we checked it is not in the literature. We also checked with we also checked with a classic solver. It is indeed not an SOS, non-negative, not SOS example. And this example, we sort of asked how and why Quinlan formed this example, and we found that it is constructed from well-known examples and constructed by observing the structure and using the theorem they learned to construct it out this kind of NSOS polynomial. Okay, so I will stop. I will start to conclude and stop. Basically, I talked about mostly in the talk is about my past PhD work, theoretical work of how we prove that a sufficiently regularized non-negative quartic polynomial is SOS exact, and how we form a globally convergent framework so that it contains trackable SoS or SoS-convex subproblem solvers. This kind of problem, it gives a structured SDP formulation. So this Q matrix. So I guess like people in the community who are familiar with the SDP formulations, I think that there may be area we can work with to look at how this Q matrix, can be maybe breaking up into smaller blocks, maybe pruned so that we can solve more efficiently. And the second part is that we have started a little trial of how to use AI-integrated approach, Siri-guided, to improve scalability or improve, like the selection of the sum of square cones. So this part is an ongoing work I am doing now, and I'm very interested in it. So also, like, I would really happy if anyone from the community have any ideas or have any collaborations going forward on those ideas. Okay, so these are the list of the papers that I sort of like talked a bit. There's two blue ones are the one I talked, and others are papers that I published or under review in my PhD. Yes, I will stop now and open for discussion and questions.
Thank you very much, Kate. Questions?